Howdy, this is Jin Tong from Texas A&M, and I'm an assistant professor from the School of Performance Visualization and Fine Arts. And my background is physics. I've been doing a lot of work on numerical activity and numerical modeling. Recently, I started working on digital twins, data science, AI, and it's great that I got this opportunity to learn Rust and also share with you all my learning experience. So since we have about 2.5 hours today to get together to learn on how Rust is working and on the ACES system, I hope you all, put away your phones and other things, just focus on the materials I put together today. And to get started, I want to acknowledge the support from ACES program by NSF, and also our collaborators from TAG and Illinois. So with all that, let's get started. So we all have about 4 parts for this short course. We started with the ACES system. We'll spend probably 10 to 15 minutes to get everyone on the ACES system. And we'll then talk about why and what Rust is. And part 3 will cover some basics of Rust. And part 5 will be some advanced topics in Rust. Since myself as a programmer, and mostly C and C++, CUDA, and Python mostly, that's my programming background. And I assume you all have some programming background. Otherwise, it's kind of hard to get you all started with Rust, which is a little bit different. I'll get into the details in a second. So first, let's get into ACES system. So we have a video already recorded about ACES, and I believe George and others have been prepared, slides and training materials to get you all started on ACES. So to get access to ACES, a quick link is to go directly to the HPRC website. There is a top-down menu called the portal. And you click the portal, you get to the item list. You can find ACES portal. I'll get you all there in a second. And after you click the portal, it will point you to a login interface. And that's where you can log in with your ACES credential. And you need an account, of course, to log in there. I'll get to the next slide, and then we'll get to the website and get you all started to log in ACES if you haven't. So after logging ACES, there is an menu item called clusters. And you can click there, you can get access to the shell, get a shell access. It's a web-based shell access. And that's exactly how you will see after you log in through some ACES terminals or some other terminals, depending on the platform you're using. But this web-based interface makes it easy for the server side to give access to everyone just through the web-based interface, which is very convenient. So with that, let me get back to my screen and get you all started. So the website I'm getting to is hprc.tamu.edu. If you see this page, you are there. And you saw from the slide, there is a menu here called the portal. If you go all the way down, there is one ACES portal, and you can log in the ACES through your ACES credential. So this is what my login page looks like. My login page looks like, so I can get in there. I'm using my ACES CI credential to log in. So I just click log on. It will ask me for my password and my login account, and I'll click login. And I'll ask for my, okay. Probably, okay. I have a fingerprint reader, so it can just log me in directly, which is pretty convenient. So after you log in, this is a website you see, and there are multiple links. If you want to explore them, you can explore them later on. But today, I just want to show you all that we can have access to the shell of the system through the web-based interface. through these clusters and ACES shell access. If you click it, it will point you to the interface. Okay. That's the first step to get on ACES. Of course, if you have terminals, either on Mac, Windows, or Linux, you can directly log in through the SSH command, SSH to the ACES system. So what we'll do after you log on, Rust is, it's not like, I'm sorry, I'll get back to that later, but Rust is a little bit different from other languages you might be familiar with, in the sense that you have to compile it and run it, kind of like a C or Fortran code. So you need to compile it and then make it kind of like a little bit extra work to run all the examples. For Python, we can use a GPU notebook, which is interactive. You can type in and you see the results right back to you. But for Rust, you have to get your code edited or copy pasted and save to a file and then run a compiler, Rust compiler, and then compile it, and then you can get the results back. So for today's tutorial, because it's an introductory level course, we'll be focusing on the very basics of Rust. So we'll be not using this interface directly, but in the future, if you want to run Rust on ACES, this is one way to get you there. So with that said, I'll go through the slides about ACES, so then you can get more familiar with the system if you haven't. And then we'll get into the Rust, and we'll be using the Rust playground and for most of the materials today. So talking about ACES, we have to go back to understand the difference between some common HPC systems and HPC for AIs. Traditionally, when you want to run AI applications, you will be using GPU, CPUs on your computer. You get your model compiled, model trained, and then use it. But for the HPC systems tuned for AIs, you want your system to be more configurable, in the sense that you want your system to be able to run on multiple GPUs. And those GPUs should be easily accessible by your software. And you want your system to be expandable, in the sense that if you want more memory, you can directly assemble a hardware configuration based on your needs. And by doing that, you can have more computing power and more memory to access to for your data processing and model training. Common HPC is kind of hard in the sense that it has a fixed configuration, and you have to utilize some parallel programming interfaces and make the coding part harder. With the configurable HPC systems, your software development ecosystem will be much simpler, because the composition and expansion of the system will be more, could be relying on the hardware side. It's a composable system that ACES and faster, which is another composable system that HPC is managing. The basic idea is that we use a liquid fabric that, based on your needs in your configuration file, more or less like your job script, you can ask the number of GPUs you need. Traditionally, I think the maximum GPU I ever used on a big system is about 8 GPUs in one server. I'm not talking about the NVIDIA specified, those NVIDIA servers. I'm talking about the traditional HPC systems. 8 GPUs was the maximum number of GPUs I can use for one single node. But with Liquid Fabric, you can put many, many GPUs as far as the system supporting. I think there is a upper limit about 16 or 24, I forgot the exact number. Someone can correct me. So you can put all this GPU together in one virtual node, and you can run your job directly. That's a major difference between this configurable or composable HPC systems compared to traditional HPC systems. So again, the scheduling system needed to be reconfigured to support this kind of system, but fortunately, working together with the company and the scheduler provider, HPRC is able to do this and offer the service to the users across the US. And you can get started on this by getting an account on ACES. So again, the accelerators are not just limited to GPUs. You can use IPUs from GraphCore and also vector processors from NEC and also some other accelerators you may have access to, and you may find on the market, like FPGA from Intel, etc. So as I mentioned, there are two composable clusters that HPRC is managing, and ACES is the one we'll be using today. And Faster is very similar to ACES on the system level, but they have different size and different focus for two different systems. So the ACES goal, I mean, again, this is as a funded project. So in the proposal, as well as the the mission put on in the project objectives, is to utilize this composable system as AI testbed to serve a larger research community across the US. And it's also provided, the team supported by Natural Science Foundation is also providing consulting, technical guidance, and training to researchers. And this short course is part of this program to provide access to latest computing technologies. So ACES is currently located at the West Campus Data Center. It's one of the state-of-the-art data centers here, managed by the IM system, and we have multiple systems there, and ACES is just one of them. And so this is an overview of the ACES configuration. We have multiple front-end. User can log in and test their code out before they send their final executable to the backend for computation. So the network is connected through the NVIDIA. Back then it's a Mellanox, now it's NVIDIA NDR InfiniBand technology. Up to some nodes are supporting up to 100 gigabytes, some nodes 200 gigabps. I'm sorry, and those are pretty decent network connection. And if you want to transfer data, there are special data nodes you can use to transfer data to and from the system. So this is an overview of the ACES system. I'll now get into details. You can find the information online as well. And as I mentioned, this is the list of all the accelerators that ACES is supporting. And you can refer to the details about the hardware by following this link. On the software side, it's completely configurable, but these are providing some basic supporting system that are helping with the job management and sharing. For individual software system that the user can either install on their local system, on their local space, or they can send a request to the help desk to install it on the system at the system level. And these are different summaries of the accelerator. When that's the special partition that you need when you submit your job, and you can refer to the other slides for ACES system to run your job if you want to use some of those actuators. So here comes a job script to run ACES and run on ACES. This just shows you one sample to run on GPU for just using one node. And you can request up to 488 gigabytes of memory. And this is more or less the example sample script you can modify. And your job, your script will be mostly getting to the end of the script. The top part is a configuration of of the system, of the resource you are requesting. And then you load your modules to set up your software environment, and then you run your job. That's basically the structure. you can follow the details in the video I mentioned previously. To run Rust on ACES, we first need to find the module the right module to load for running Rust. There are multiple versions of Rust installed on our ACES system. The command line to find the modules available for Rust and some other software is simply you run module spider. That's the command you use to find a certain software. Here, we do the module spider Rust. You can see a list of Rust installed. And then we are using easy build, which is a hierarchical, like there is a dependency for different modules when you load them. The next step you do is to do the module spider, the particular version of the Rust. It will print out all the modules needed before you can load the Rust 1.82.0, which is the latest version of Rust, stable version of Rust you can find on the Rust website. As you can see, there is a GC core, which is GNU C compiler core is required for Rust. So that's some module we have to load. So that's step one, find the module to be loaded. And then you load the corresponding module. Here I put a GCC core and Rust all together. So the module load will load both modules and resolve the dependency, and that's it. So after that is done, you can start run Rust directly through the shell interface. So again, there's no graphical interface like IDE installed on the system to help us to do something as fancy as the playground we'll be using. But this is how you get started with the Rust compiler and to load the modules on ACES system. So with that, I'll get back to the shell I just mentioned. Where is my shell here? So let me zoom in a little bit. While I'm typing here, if you have any questions, feel free to ask. I think we don't have so many people today. Feel free to just unmute yourself and ask me directly. I'll be more than happy to help you. And we also have some other staff members here from HPRC can help you with your questions about the system. So this is my current directory. As you can see, I have Julian and CUDA loaded. So the first command I need to do typing is module spider. Rust. It will print out a list of Rust systems. So we go all the way from Rust 1.52.1 to the latest one here. So when I select it, as you can see, my system actually is on Mac Chrome. It copied my selection automatically. So what I can do, I can just do the Control V. I'm sorry. It seems I needed to finish everything. Okay. If I do the module spider, Control V, which is when I select it, automatically copy that. If it's not working on your system, you need to Control C and Control V to copy that, or you can type in directly. Then if I run module spider, this Rust, I can use up and down key to go back to my history of commands, and then I can show them. And it shows the GCC core here, which is showing up. So next I'll do is just do module. I'll be a little bit lazy. Let's say load and Control V. So I do the module load GCC core and Rust and return. You'll see nothing. That's what you're expecting. What you do next, you can do mod ML. It's module load, which is a shortcut for that. It will show you all the loaded modules. So OpenSSL is loaded by default, and it's not something I ask you to do. I just loaded the basic requirements, and the Rust will load the OpenSSL. Probably is needed by some libraries inside the standard libraries there. So I have the 3 modules loaded, and now I can do Rust. If you can use a tab to do the auto control, you can see if you do the tab, you can see multiple other commands showing up, and you can do Rust compiler version. It will show you the version of the compiler you're using. Now, let's get into the next stage. If you're familiar with all the editors on this command interface, you can just do the VI or Nano. I believe Nano is not here. What's the other editors people use here? you can use the web-based interface to, I'll show you how to do that in a second, but I'm a VI user. You can use the VI to start editing, raster files. Okay. So it asks me to save, need a file name. I'll save it as W. So I can use C to compile my code. It will default to my name. That's how I use it. But unless you are familiar with VI, it will give you trouble, just like you see, because I have this small, tiny annotation here. I couldn't see the shell command, but that's one way to use it. Another way is to go to the portal, and you can see there are files. You can go to your home directory. If you click it, it'll point you to the home directory. And you can create a new file here. Click a new file here. It'll create this file, but then you need to go back to the shell to compile it, to run it, because this is just a file management system. It doesn't provide an interactive user interface for doing that. So this is the one I just created. If I click it, it'll open up, show it. I'm sure, sorry, it's just too small here. So that's a file I just created with my shell interface, but you can also have access to it through this web-based interface here. Okay, so this is how you run Rust on the ACES. But again, we only have this shell-based interface for now, and that's what your Rust is, kind of like a C and C++. You need to have your source code edited probably on your local IDE, and then you upload it to the system and compile and run and test it. So that's probably the most for the starting point to get you started on this on our ACES system. So any questions so far? Since we're not talking about any advanced features of Rust to do the parallel programming and other things, so I'll be not getting into the details at this point. But if you have any questions to have access to ACES, and feel free to reach out to us, and we can help you to get you started. Good. Now, for today's a short course, we'll be using if you do the Rust programming language, if you search Rust or whatever, you will be pointing to the Rust programming language official website. So this is the official website for Rust, and it's called rust-lan.org. And my materials that I prepared today is mostly based on the book here, which is a fabulous book. If you all want to learn something about Rust and get you started, this is the book to get started. It's free and open source, and you can do that. But for today's exercise, I'll be mostly using the playground. If you click the playground, which is the top menu, the third one here to the left, from the left, playground will point you to this interactive interface that you can copy and paste your code and you can run things. And I would suggest you make this. Let me see. This is how I do it. I'll create a separate window. I'll drag it out. I can move this to my left and then this to my right. And this question's okay. So you can have access to the slides. That's what you should look like. Your layout should look like if you want to fully leverage the interactive process that we'll be going through starting from the next part. So what you do, for example, if I say, okay, let's try to run the first example, you go to the slides and this is a copy paste and Control V. It will show the example here. You just run it. It will show you some errors, which is something expected because I didn't copy the paste the whole thing. So you copy and paste the whole thing here with greeting, add, and calculate strings here, and run it. You'll see the output at the bottom. So this is a very good way to get you started with this with the program language that need a compilation, because you don't need to run all the command line compile every time, and it's a very, very good way for beginners. So I highly recommend everyone to get used to this kind of interface. It's very, very convenient. So with that, I hope you all keep this kind of interface on your end, and I'll be showing the video on my end. Hopefully you all can switch back and forth and copy paste. Let me close this one. Otherwise, it'll kind of hard to see what's on the screen. So next, we'll get into Rust and covering some basics, answer some questions if you have any. Again, I'm a beginner of a Rust programmer myself, and I heard about it last year, and I started working on some cybersecurity projects recently, and working on a proposal and trying to learn more about the community. It turns out the best way to learn a community, especially in the technical world, to understand the terminology. And the Rust is a language people, especially the technical people, are saying, I'm saying or using with a double quotes here, is that because that's how they use the Rust to share their information, share their knowledge. So I think probably it's best way just to get into this field by learning a language they speak. So that's how I got started. So I have a motivation and I have a need to learn this, and that's how I came here and just start showing my experience, learning experience. So again, don't expect me to be an expert on all the details of all Rust. And I'm not working on any serious project with Rust myself, which kind of different for C and C++. I did write some code to do some serious computational stuff. But for Rust, it's mostly just exploring at this stage for me. But I think it's good for this introductory level. I can share my learning experience with you all and probably be helpful for some of you. So when I start learning any language, I just look at very simple examples and try to compare with whatever I learned before. To me, my first impression is that this is very, very similar to C and Java in many ways. It doesn't support object-oriented programming like the way all the C++, Java is supporting or Python supporting, but it does provide mechanism for you to do object-oriented programming. And the language itself has been designed to incorporate all the possible inputs that a programmer can provide to the compiler, so that the compiler will have a better understanding about the situation. And when I say situation here, I mean the situation relevant to cybersecurity, relevant to memory leaks, relevant to bound checking, or etc. If you are a C programmer, you know that the compiler doesn't do much. It's just compile code, and then you'll be running into errors when you run your code. And most of the errors you see in C or some other languages will be statically checked by the Rust compiler. So that's why you will see a lot of weird and strange symbols, definitions here and there in Rust compared to some other languages you're familiar with. But that's the hints. That's some extra explanation that some compiler is asking you to provide. And of course, not everyone knows all the details, and that's why you want to learn Rust. Rust will give you this framework about security-related issues, and you have to think through before your code can be compiled. Okay, so that's the main impression I have for Rust. It's like a very demanding C compiler, and with some extra special weird requirements, That's my first impression. But after you start getting used to it, you may see actually it makes sense. That requires you to focus more on the safety issues when you start writing your code, instead of worrying about security concerns and other things, other issues later on when you deliver your code to your customer, right? So from that perspective, I think it's something almost every program needed to actually familiar with some of the concept introduced by Rust. So that when you're writing your C code or Python code, you can put those considerations into your programming. And from that perspective, even if you're not using Rust, this is already a very good learning experience for you to deal with cybersecurity and related issues in different languages or different part of your project. Okay, look at this code. You have a main, which is the entrance for the function for the whole program. After you compile it, we know this in C and C++, Java, we all have this entrance function called main. In Fortran, you have a program. You need to tell the compiled executable where the first byte of the program is and where the entrance to execute all the binaries when the code got compiled. And you have functions, which is one of the major components for all the Rust structures. It's based on functions. So it's not functional programming, but when the people designed this Rust, the first, I forgot the name of it. I'm sorry, we'll get to his name. When the first developer for the designer of the Rust program, when they start doing this, they are more familiar with functional programming. So there's OCaml, which is a functional programming language. They were used as a reference, which are highly influencing the design of the Rust itself. So that's why you might see, especially those who are familiar with traditional structured programming background, may see some interesting and some strange definitions here and there. But when you get into the functional programming, you'll get used to that. So I'm sorry, Graydon Hoare, that's the name, who started this as a personal project when he was working at Mozilla Research in 2006, which is very new, for the programming language. And it was officially sponsored by Mozilla in 2009. And the first stable release was in May 2015. And then latest version that you will be using today, it's released, I think in October, and it's 1.82. So the Rust official website is very, very good. It contains tutorials, examples, and the best practice guide, and also the most important of all, the programming book, which is very, very good. So the goal of the Rust was just to empower everyone to build a reliable and efficient software. And the major feature of the Rust, of course, the safety and cybersecurity concerns were put into Rust in the design at the design state. And also because it's a compiler language and kind of like C and C++, it's reaching almost the native, I would say like C or C++ level of performance. And if you use C and C++ as a candle, right? Usually, Fortran, C and C++ give you the best performance because the compiler has been highly optimized to do all the computational tasks, etc. And Rust is comparable to those very high performance languages. For the memory control, it has efficient memory management, but again, the ownership and the lifetime, all those concepts that do require your input for you to have a better control of the system. So you have the power, but you also have the liability to provide the information needed by Rust for it to run what it should run. So again, it's always a trade-off. Some convenience always, be sacrificed for certain more rigorous check for safety and security problems. And productivity is something, subjective. Some people may consider some of the requirements might be too strict. Some people may consider it's okay. And again, now with AI helping us, and productivity is probably we need to talk about at a different level, because if our it's I'm sorry, not R. It's a Rust community. It's providing all the open source tools and documents online, freely available. Like in the last several years, probably more than 10 years, about 10 years. The AI system, the larger models can capture that, can easily turn that into helpful instructions. So that's why a lot of examples I use today, I generate those, I check those, and I did learn through this AI generated examples a lot myself. So another big reason for me to get into this is the whole community push to build the safer and more protective software environment. Like DARPA, probably you all know DARPA. It has a recent program just released. Actually, it just passed. The program, it kind of has a very interesting title. It's translating all C to Rust. It's called Tractor, very nice abbreviation. And the whole project, the whole funded project is to ask those who proposing this this project to find the innovative and efficient way to translate C code to Rust code, and to solve those memory potential memory and safety issues. There are two white papers I also noticed when I started preparing all this all the a different proposal. And one of them is from the DHS CISA report, and it's trying to explore in different ways, and memory safety might be affecting the ecosystem, not only the ecosystem, but also the infrastructure. Because nowadays, when we talk about infrastructure, it's both hardware and software. We have a software infrastructure, we have hardware infrastructure. The software infrastructure actually getting more and more important nowadays because they have control over the hardware infrastructure in many cases. And being able to safeguard those software infrastructure is a big concern for DHS. And also in 2024, there is a white paper report. Probably some of you also read about it. It's just a couple lines of statement saying that Rust compared to C or C++ is ready for taking care of some of the software issues, but it's not ready yet, in the sense that we don't have the large enough ecosystem like Python or C to turn Rust into like a foundation for building all the building blocks. As you may see from your own experience, Rust has a relatively small community compared to Python. Python is huge, mainly because AI and data science. But now with the cybersecurity being a big concern for the society, and I believe in the near future, Rust will probably have played an important role, just like what Python is playing for AI. So again, as a programmer myself, starting with a Fortran, C, C++, Java, and Python, and now I'm trying to learn Rust. The first thing I do is to see what how they compare to each other. This is not an exhaustive table, but I think it at least shows some major difference. The main difference I see between the let's say 3 languages is that the memory management, which is it's a major difference from my perspective. Python has automatic garbage collection. As interpretable language, it's handling all the dangling memories and itself. C++ give you, and C, I'm sorry, C and C++, not just C++ here, does give you the freedom to manage memory yourself. You either use new, or you can use a malloc to allocate memory, and then you handle those and you free them. Sometimes you forgot. In many cases, it's the system will handle that, but in some cases, very special cases, if you don't free or free twice, you get some problems. And another one, I think it's more about the error handling, because most of the issues in C and C++ is that the compiler doesn't do a very rigorous check as far as the memory and all the exceptions are concerned. It's rely on the user, experienced programmers, to deal with those issues. The same probably for Python, I can say that, but for Rust, it's it's trying to do the static analysis before you get the executable compiled. So any potential errors could be explored on the source code level. And that gives you the control over all the unexpected scenarios. And at least you have some help from the compiler side to check all the potential issues that you might not be aware if you are using C++ or Python. That gives you the power, also makes the programming a little bit more, I would say, complicated than Python, especially. Rust has its own standard library, and it will go through some of the examples today as well. But as you may see, it's just very minimal. It provides some basic functionalities, but it does give you the tools to get you started. So that's why we need to build a bigger community based on these tools. This standard libraries to build more powerful tools for specific domain, and to make this Rust community more helpful in makes the Rust ecosystem better for dealing with different issues. Another one is about a type system, and Rust is a strong static typing, and Python is a dynamic typing at runtime, and C is a strong static typing. So from this perspective, Rust and C are very similar. Learning curve, the last one, learning curve, I would say Rust is a little bit steeper. You needed to have some background in not only the programming language side, but you also need some background in hardware to understand how the hardware works, how the, for example, the heap and the stack memory work, and how the operating system handles different exceptions, etc. Which is something that you probably don't need when you're writing a Python code. But in C++ and C, you deal with all the pointers, memory handling yourself. You should be able to understand the basics about hardware itself. So with a background in C and C++, I think you can get started with Rust pretty quick. But Python, if you switch from Python or if you have a Python background, it's still same. The syntax are very similar across all these three languages, but you may feel some learning curve there. So again, in addition to the playground I showed you for the online interface, you might want to integrate all the plugins for your IDEs, your favorite IDEs to get started. I don't use the VS Code myself, but I have students that do use this on a daily basis. They're highly recommended this to me a couple of times. I do use a PyCharm, and actually it's developed by it's a commercial, and also they have a community version which is free. It's by JetBrains, which is a very, very popular IDE developer. They have IntelliJ and many other famous IDEs developed to the market. Rust IDE is one of their latest product, and you can see they have the IDE and incorporating into their standard interface. It's very similar to PyCharm. It feels very user-friendly to me. So the one we'll be using today is a Rust Playground, and you may have trouble to do the interactive because you cannot. I don't remember. I don't think you can type anything in during the runtime because this just run your compiler code, so you won't be able to interact. For some of the examples I tried before, it requires the input, but I don't think you can get input here. But again, it's very good for you to quickly explore the code. Sometimes, after you generate some code using ChatGPT or Perplexity, you don't know if it's working or not. The quickest way to test that is just copy paste it directly to the Rust Playground and try that out. So again, I'm not against AI to generate code, but just like when you try to learn something, it's good to use AI to help you with some guidance, but it's good to learn from the basic syntax. Being able to type in some code and make it work and make you feel pretty accomplished. Copy and paste is working, but it's just one way to get you somewhere, but it's not the ultimate way to get you to know and remember something. So one of the major lessons I learned in the last many years of as a programmer, if something you can directly copy paste, you'll forget about it quickly, even though you tried harder to memorize it, but you won't remember it because your brain has been, in the so many years of evolution, human's brain has been trained to forget the things that can be easily get. If you get something through some effort, you'll learn it. Okay, so that's from my own experience, but different people might have different opinions. So this is a book I mentioned. They released the second version, probably the second version of the book, edition of the book in 2021, and it might be using some old versions of Rust, as I would imagine. Some of the new features might not be mentioned in this book, but again, it's already pretty good starting point for you all to get started. Since the Rust programming language book itself is freely available online, I would suggest you just get on the online version, which I believe that one version is more up to date to all the changes in the language itself. Hard copy is good, but just in case you meet some new features you may need in your project. And okay, before we get into this part 3, any questions? So again, a lot of things I mentioned previously might be biased. It's just from my own perspective, but just consider it as some tips you might get, but doesn't mean that you have to follow that, right? So again, as C and Python programmer, the first thing I try to get into this language is to look at the basic data types. It does support integer, float, bool, and char, which is standard, which is nice. That means I don't need to learn that hard. There are some signed and unsigned integers and different floating point types, F32, F64. You have different names for different languages, but they're essentially the same thing. So nothing to worry about here. You have a bool here, true, false, good. And you have character type, which is also good. It supports Unicode, not all the Unicode, but it does support Unicode as for its input. It does support all the Unicode for its data, but for variable names, some of the Unicode they cannot be used as a variable name. We'll get into that. So it's good so far. If you're familiar with Python, C, similar. It's just some details, some names like I32, or you use you have different symbols representing that. For compound types, you have enum, which is a enumerator, which is something common in C, and you have tuples, which is good. It's just a combination of the different data types, and you have arrays, which is also pretty common in all the languages, and but that's not all. This is just some common types that Rust have by default. But you can also build your own component types. I'll get back to that a bit later. So enums in Rust allows one to define a type with a combination of different scenarios of different variables, make it easy to model different state. That's what enum is mostly used for. The same for Python and C, and we have a similar structure easily. So for custom data types in Rust, it's use a struct. For those who are familiar with C, this is exactly what C is using. It's just like syntax a little bit different. You don't need to define your types of your members of a struct like this. You put an int in front of X instead of put a column and then integer 32. But basically it's a similar structure. You have a struct, exactly the same word, keyword. You can define a data type like that. And then you can initialize it. You can instantiation of this structure and create an instance P1 here. This let is something new in Rust. Probably you're familiar with Java. Probably it's not something new or JavaScript. I forgot JavaScript or Java. It's something people use that to define a new variable. And Rust does require you to use let that so that Rust knows that this is the new variable you want to define. Instead of assigning some value to P1, you are defining a new variable P1 here to hold the information to the right. Okay, that's why let is actually needed as to tell the compiler that you have a new variables introduced to the program. And again, Rust doesn't have a class, which is kind of interesting. It doesn't have a class. It just have a structure to define the data. Okay, so it's not designed to do the objective programming from the beginning. It just defines a data structure for you to play with. Now, the struct itself, as I mentioned, is very much like a struct in C, and it doesn't provide the methods. If it does provide a method internally as a part of the struct, it will be a class, not a struct. Struct itself is just like a table, nothing more, nothing less, just holding the data. But Rust define traits. That's something I'll talk about a bit later. You can use that traits and a structure to define your own object-oriented programming objects. But by default, it doesn't define that class kind of like a, type. So the fundamental parts of the Rust type system of Rust here is a struct. People use a struct to build a complex data set and data type, and you can define your data type like that, which is good to get started. And but again, people who want to use something like a Python class will be disappointed a little bit, mainly because that's not something that the Rust is providing. Now, to provide the method, it's not doing this as a whole class structure. It's doing it separately. So it defines this data structure called a point, like in the example here. And then you define a function associated with a particular structure. So you want this function to leverage this data structure and change that data structure to a different state. That's exactly what object-oriented programming is about. You have an internal function that changes the state of the object to a different state. By doing that, you have a full control of the object, right? But here, Rust using implement IMPL, which implement this data structure, and define a function move by, and this move by is taking the input data and modify it. So basically move this point to a new position. That's what this example is doing. So I'll stop here for probably a couple of seconds, probably 10 or 15 seconds. You can copy paste this to the playground and you can run this one. So I'll also do this myself. What I'll do is just Control-C. I'll go to the playground. I need to create a new playground. Okay, let me. So we start with 5 and 10, and then it's go to 8 and 14. So that's basically what it does. It's supposed to be doing. I think there's a question here. Oh, I already shared the link. Probably if you joined a bit late, let me see if we have the link somewhere. I believe it's this link. Right. So this is the slides. You can have access to it. As I mentioned, you can put this playground to the left and slide to the right. Then you can just copy paste. Well, listen to me. Okay. Okay, let me get back to the slides quickly. So again, these are already advanced features, but I just want to show you that for those who are familiar with Python and C++, we do have something like this to implement classes, but it's not in the one structure class. You do this separately. And you do this separately. I think the argument from the Rust perspective is that now you can define your functions, can support multiple structures. and they have the interface defined. As long as you keep the interface the same, doesn't really matter if your structure has this method or not. The method will be implemented by other people or yourself later on. So that's argument. That's something I found online. So name of the structure must be the same as name of the, yes. So it must implement this structure, a function for that structure. So it's trying to implement this function for this structure. That's what it means. So we'll get into that a bit later and with more details. But here are just like a teaser for you to get into this data type. Now, after you understand the basic data types, integer, float, char, and Boolean, all those values, you start to define variables. As Einstein mentioned, those variables are the most fabulous thing in the whole universe, in the math, in the math structure, and in the whole universe, because you can have everything defined for the variable. Give me X, I can have the whole universe inside this X, as long as you want, right? And you have this variable that can hold anything. On the computer, this variable have to be some data particular type. And Rust is a very strong type. It checks the variable in the static during the compilation time, not during the runtime. It tells you if this variable is defined or not, and if this variable has a type or not. So when you try to do that, during the compilation time, Rust will help you to do the inference for the data type, but it will be strongly checking the usage of the variable to see if the usage of the inferred data type is consistent. What I mean is that the statement I put in here, like let ed equals 25, you don't put I32 here, define this ed as an integer, I'm sorry. So Rust will infer that, but this inference is static. This inference during the compilation time. And then it will keep checking the other part of your code to see if your edge is used as an integer. If it's not, it will give you the error. So by doing that, it saves a little bit typing in the program itself. But again, it does do all the inference and all the type checking carefully for every variable in your code, which is a very good thing. At least, for me, I think it's a good way to get a safe code and defined and written. You need either programmer to check everything carefully, which is not so reliable, or use a compiler. In my opinion, I think it's more reliable than a programmer. So the variable must begin with a letter or underscore, which is almost the same for all the languages we are comparing now, C++, C, or Python. And the names can include any combination of letters, numbers, etc., which blah, 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 it's the same. And then the Unicode character could be used as well. I used that when I was teaching Julia. And we can do the interactive program. You can see we can use Unicode, we can use a football as a variable name. You can do something crazy with that, which is very interesting to see how things are working. The same here with the Rust, you can use Unicode as your variable name. I believe Python, later version of Python, do support Unicode as well. You can check that out, but not in C. And I'm not sure about the latest version of C++, but C definitely not.
Can I ask a quick question about
yes,
variable?
go ahead.
So I know that, like in Python, if you wanted to kind of signal that, let's say like a method or a variable is meant to be a private variable, then you would do like an underscore
Yes.
in front of the variable. Is that the same norm in Rust, or is it just that kind of a coincidence here?
It's a norm in Rust, exactly. So basically, when you want to say this is like an internal, but it doesn't have a very strong meaning for the compiler itself, but it's more or less like a hint. But double underscore has some strong meanings. We'll actually have one particular slide for that, so we'll get into that. Yes, those for the private, public, protected, those are pretty commonly used keywords when defining members in your classes in C++. Here, Rust is using the lifetimes and ownership. So it doesn't use those keywords to define the scope of the membership. So we'll also get back to that a bit later.
All right, thank you so much.
Sure. So for the variable names, there's no explicit defined maximum length, which means you can use very long variable names. Not so many programs are trying that, but I never tried how long I can use this name for Python either. Probably you can use a very long names for Python in Python as well. And Rust is case sensitive. Now there's not so many languages not case sensitive. For example, Fortran, I think MATLAB. What else? Let me see. What else is case sensitive? Basic, I believe Basic. Pascal, I forgot your Pascal capacity. But of all the languages I either familiar with or heard about, not so many languages are case sensitive. So just assuming capital case and lower case are different in Rust. And the variable name should be descriptive. And again, here means you don't want to have a double underscores in front of that, mainly because Rust does have a special rules for double underscores. When you have those double underscores leading the variable names, it's treated as an internal variable. Sometimes you might have a conflict there. So it just prevents you doing that by detecting double underscores, and you'll give your error message during the static analysis stage. So one major thing about, I would say kind of interesting here is that all the variables you define by default, it's immutable, which is quite interesting. Basically, when you try to define a variable without any mut, M-U-T, a keyword, Rust will treat it as a constant or like a parameter you cannot change. So if you do this, let ed equal to 35, and then sign ed, let ed equal to 36, you'll get error. And that's actually one of the main features to protect this ownership and other things. We'll get into this later on. By defaulting this, so no one or even yourself cannot change it. Now let's like give you the default protection of all the variables at the system level, at the source code level. Basically, this is done through the static analysis. It's not during the runtime. It's during the compilation stage. It will detect this error and tell you cannot do this. Okay. Now, to make this mutable, you have to manually turn that into a mutable variable with MUT. It will you'll then be able to turn that ed into a new variable. And then when you run this, you also get a volume message saying that, hey, ed equals 35 since the value was not used. Because when you change that ed to 36, the 35, this initialization value is never used. It will give you a volume message at this compilation stage, which is also nice for you to see, there might be some potential problems. You want to initialize this value to a certain value, but you never use it. What's the point of initializing that, to a certain value, etc. So again, immutability promotes safer and more predictable code, and always a good thing to be more defensive on the programming side. And immutable data can be safely shared across threads. Again, so those of you who have been working with parallel programming, either using multi-threading or multi-processes, the last thing you want to debug is your thread racing problems, and those are just so hard. I mean, people are saying that the threads are evils, right? I do now consider it's a truth. It helps for you to maximize your performance quickly, but whenever something bad happens, it's kind of so hard to figure out the problem unless you have a very rigorous threading, thread safety procedure followed. But of course, in many cases, people just want to get things done quickly, and then something happens, you have to figure out how to resolve the problem, and that's time consuming. This is something Rust is preventing you from doing by defaulting everything into immutable data. As long as you are not modifying this immutable data, you are thread safe in the sense that you're free to change anything because the data itself is not mutable. You don't need to worry about any other thread modifying your particular variable, and you can just go forward and do the multiple threading safely. So that's one of the major issues actually for C, and I'm not sure about Python. Maybe Python have the similar problem. And people have been trying to figure out different ways to fix this, but again, Rust solved this problem from the source code level, from the very low level, and from the programmer's perspective, it's preventing you by making those kind of mistakes. But again, you have to be careful about your variable to see if it's mutable and unmutable. But at least that give you one extra protection. And I also already mentioned about the type inference. So if you give me this variable, if I don't declare it to be say integer, it will infer from your input. If I do put a particular data type there and modify that variable with another data type, it will give you an error message directly. That's again during the compilation stage, and it's kind of interesting because in C you can only see this error, in most cases, depending on probably some preprocessing or some other extra features you're using for the compiler. But you probably can only see this during the runtime when the system gives you the error. Sometimes it's just do the dynamic casting. You won't be able to see this error because it's casting your data into the data type. But sometimes you don't want the casting to be happening, because when you're casting a floating point into an integer, you're losing the accuracy. Everything behind the period will be dropped, and then you might be making some mistakes. This kind of system will help you to preventing those kind of scenarios by doing this type inference at the compilation stage. Okay, so shadow is another term I learned. I never heard about this, actually in the context of programming languages, but shadowing here allows you to declare a new variable with the same name as a previous variable. Well, I mean, you might think this is kind of weird because when you assign a variable edge to itself, right? Basically, you are killing the previous edge, and then you get a new variable defined, and then you use it. So the new variables shadows the previous one, and then the previous one will just throw away. The system will forget about it. Probably during the compilation state, it's able to handle that because it's noticed that the edge was reused, and then the previous edge is not used at all. It will just completely get rid of that extra variable defined in your previous statement. Like in this example, you can copy paste it yourself. You'll see how it works. Now you define this edge as a variable holding it's an integer holding this 35, and then when you let edge equals edge plus 1, it's not like the previously problem. As you may imagine, you'll use the same memory address, and then the value of the edge will be added by 1 and saved back to edge. That's not the Rust is working. So Rust, at least on the I don't know what's the backend is working. On the source code level, what it does is basically it will define a new variable edge, and then it gets the value from edge and plus that by 1 and save that to this new variable and throw away the old variable. That's what Rust is doing, at least on the source code level. I don't know if it's reusing the same memory, I'm not sure. Probably it's already get rid of the first statement during the compilation stage. So you are directly getting into the second stage somehow. So I needed to learn more about that myself. But as far as what the Rust programming guide is telling us, this second edge is a different edge. It's not the old memory that holding the same edge. So that's some difference, conceptual difference that a C programmer or Python programmer needed to get used to. Okay. I assume it makes sense because that's why I mentioned this late is actually important. If you don't have this late, it's a sign statement. But now with this late, you are defining a new variable. Okay. So sometimes I think, when I get started, I think this late is kind of redundant. But now if you look into this definition, you may see it's explicitly define a new variable actually. So it makes the whole syntax definition more consistent with this extra late keyword. This is called a shandle. Okay. So there are some primitive data structures like array and a slice. Array is it's just a regular array, like a list in Python, and array in C and C++. And a slice is just a one way to dynamically grab some part of it. If you look at this symbol, those who are familiar with a C, it's or C++, it's a reference symbol. It's just trying to get the address of the second element, because one here is zero indexed. Again, this is zero indexed. So Rust is zero indexed. So when you do the array with a square bracket with 1.3 as the last line on this slide, you're trying to get the address point to the second element of that array. Assuming you're familiar with this reference symbol. In Rust, it's not, actually this symbol is not defined as a reference to grab the memory address for the second element of this array. It's trying to, how I say, it's trying to find the linkage to the size of view into this continuous sequence. So it's to define this reference. I'm sorry. Let's define this particular element to the right side of this equal sign as a new content, and save that content into this slice variable. It's like a part of the big array. That's how Rust deal with it. It's not like what C is using this reference symbol for to get the memory address. It's trying to get a piece of the array and save that into a new variable. So that's the syntax I got confused at the very beginning. When I look at this, okay, it's straightforward. It seems to be doing exactly the same thing like what I'll be doing. But remember, when you have C and you use this reference, just this reference will give you just the starting memory address of the second element. That's the address of memory. That's what you save into slice if you are using C. But with Rust, you have the whole array taken from this original array ARR. You're taking the first to the second to the third element from the array and save that into the slice. So slice has a bounded array. It's not just saving just a single memory address for the starting element. It saves the bound of the array. That gives you the power to do the bound check, to see if your array is going out of bound. That's something that C doesn't provide, which is actually a very common made mistake when you try to do to find the corresponding address for one element of the array. You don't know when this array will be ending. You have to pass another number like n or whatever, a variable, so that you know when this array is ending. And the Rust is doing that automatically because this array is already defined. So you can do that when you do the slice, it slices the piece of the array for you. Okay. So these are some built-in data structures in the standard collections, and as you know, many of them are kind of very similar to what Python and C++. There is a C++ standard library and providing similar structures. But I'll not get into details about all this. When you need it, you can get into the documentation and figure out how to use them. So we talk about the data types. We talk about variables. It's kind of like when we are learning different languages, natural languages. We start from syllables in letters, actually in the English. We learn letters, we learn words, right? Those are like variables. Then we start using these words building sentences. Before we building sentences, building some phrases. Those phrases are more or less like expressions in different languages. In C, C++, Fortran, Python, you have expressions. Now, with expressions, you can build a full statement or sentences in natural languages. And with those sentences, you put those sentences together, you can build a block of sentences. That's more or less like function. And with all those blocks of sentences, you can build your whole program. So it's this level up kind of hierarchical structure. And after we learn how to write down all those, after we know the variables, we can start writing statement to assign values to the variables and then start building something more interesting. So let's start with all the comments. Rust comments kind of like a C++ or C. I mean, the ANSI C, it doesn't support backslash, kind of the slash, backslash. This is slash, double slash. But in latest version of C, compiler does support double slash as well. So you can use double slash or this blocked comment, multi-line comments, which is a slash star slash, give you the multi-line comments, which is similar to C and C++. You can also put a double slash at the end, towards the end or somewhere, anywhere. It will be treated as the comment. Anything behind this double slash towards the end of the line will be treated as a comment. So straightforward, that's a comment. And then the semicolons, that's required actually. Semicolons are required. You can see some parts that don't have semicolon, but those will be evaluated by the system as expressions. Those expressions need to return some value, and then the value need to be returned. And we'll see in the implementations of those functions, you can just get rid of the semicolon in the last statement of your function, and that the results after you evaluate that expression will be used as a return value for the function. So that's when you don't need this semicolon, but in all the other cases, you need to use a semicolon as an indication of the statements, end of the statements. That's exactly what a C is required. You have to use semicolon in C as well. So if you don't want to show the output of the, for example, the last line here, if you don't put the semicolon, it will need to return. But if you put a semicolon here, it just suppressing the results. System just ignore the output and nothing returned because you don't have any return statements there. It's just threw away to the, to the null, and no one will, it will not be printed out to the standard interface. Nothing will be happening. It's just suppressing all the results. If you put a semicolon without anything to the left to assign this value to, you put a semicolon to x+1 at the bottom here, the system will just ignore it because nothing will be holding the value for that unless you put something to the left. That's a semicolon. And then, like most languages, you need to do all the numerical numerical computational stuff. This arithmetic operators will be definitely useful. And these are the basic operators: plus, minus, multiply, division, and mod. And those are just following, exactly the same order of priority like many other languages. Everything we learned from elementary school should be working just like that. And this is just a simple example. Or some of you may see this print line. There is a explanation symbol here. Actually, it means it's a macro. It's not a function. So this is like a macro in the C or C++. You define as a wrapper for functions. So what it does, it takes your input, everything inside of your parentheses, and parse that, and then process the corresponding value and send the corresponding value to certain functions. It will then give you the final output. So print line explanation symbol here, it's just a macro. So you have to use the explanation symbol. Otherwise, Rust will consider print line, print ln itself is a function, but it's not. There's no such a function. So you have to use the explanation symbol to get the whole line printed, and also it will insert the extra new line symbol to you. if you are familiar with this Java, I believe have this print line function that you can print this statement together with a new line. That's a print line. Okay, so this is a straightforward mathematical computation. And again, as you can see, we use a LED. The Rust is doing automatic type inferencing. So sum will be automatically assigned to integers, difference will be integers, product will be integers, quotient will be float. So that's done by Rust at the compilation level. So these are some of the relational operations. When you want to do any comparison, we build up your conditional statements, and we want to have this criteria want to use to evaluate certain loops. Whenever you want to break a loop or continue the loop, you need this relational operators. This is the operator collecting different expressions to build up your statement. And you can overload them, kind of like, I believe, Python and also C++. And I believe when I was teaching Julia, you can overload all these symbols to do the things you want. So then these symbols could be doing different things for different data types. And the same to plus and minus, you can overload them. I'm not sure about I believe the plus minus sign might be overloaded as well. So I haven't checked it, but for the comparison, it definitely, you can overload them by defining different traits here, which is like interface, implement this function for this equal, double equal, or greater, less than. Implement the function you want to use this symbol to represent a particular operation inside for your particular data type you define. So this is very similar to what Python and Julian and other, even C++ can overload the operators as well. These are Boolean and bitwise operators, and these are also standard, almost, I think it's, I don't see, yeah, all these are just standard C and C++ symbols. You can use them for the operations. One thing kind of special that I noticed also for Julian, which is kind of different from Python, is that not a number here, is not equal to any value, including itself. And it's kind of interesting to see how this is utilized, because I believe both Julian and Rust, they are following the IEEE standard to define these two symbols. Python, I believe, is doing something similar, but I don't think it's doing something like this, at least for the infinity. I'm not sure if it has this constant. I haven't tried that in Python myself. Someone can try it. So there is a very special symbol called infinity. You can define positive and negative infinity. The inverse of infinity is 0, and the inverse of 0 is infinity. It's not a line, but it will differentiate between line and infinity, which is sometimes it's usable, because when you have a very big number and you want to have, you want to represent that, infinity might be a good way to give you some theoretical limit that you can do some comparison. I don't know, people might be using this in different way, but 1 or 0 and 9, they are different in some cases. And but here, at least following the IEEE standard, we are trying to differentiate between NaN and infinity and during the programming stage. So these are some mathematical constants. I put a floating point 64 bits here, but the same function could be working with 32. All these are mostly floating point operations, and they have some constant defined for 1 over pi, 2 over pi, etc., which is pretty commonly used in numerical computations. There are some other constants defined here. You can look into the table too. Not this table, probably on the programming book, you should be able to find the appendix and contain all the constants defined. These are built-in math libraries. Basic arithmetic operations are shown here, and then you have a power, exception, sine, cosine, and all the other functions. Those are standard math functions that you can probably see. You can see all those in standard C++ and C and Python math functions is very similar. I think for some miscellaneous functions that might be different here, but all the others you can find similar functions in other standard libraries. Okay, so we talk about variables and mathematical operations. Next will be expressions and statements. So expressions evaluate to a value. Give me something I evaluated, but it's not it's just an evaluation for the certain expression. But it's not a statement itself because it's not a complete statement as far as the Rust is concerned. For example, you can say x plus 2. So the Rust will consider that as an expression to evaluate that correctly. But if you don't assign it to any value or put some statement or something wrapper around it, it's not a full statement from Rust perspective. So a statement perform actions, but do not return a value, and expression evaluate it and then return a value to the scope outside of the to the expression. Okay, so if you look at this example, so you first set x equal to 5, which is good, and then which is expression, the literal x with expression, and then x plus 2 itself is expression. But when you let y equals x plus 2, you write a full sentence. Full statement. And then whatever to the right here, you may consider expression, but when you get the whole statement, legal statement written in the Rust, your expression itself will be getting the value assigned to some, either returned through the function call or saved in a variable. Otherwise, your expression itself doesn't really do anything. So you can have a holding multiple expressions, and this block itself can work as expression. But inside that expression, you can still, it's a collection of statements and expression, which is more or less like a nested expression. You can have a block defined and evaluate multiple statements, and then the return value needed to be evaluated by expression. If the last statement here with y equals to x plus 1 in the function above, you'll have nothing returned. So itself won't be working as an expression. You may say similar things to Python and C++, but here it's just explicitly telling you the difference between expression and the statements. In C++, every statement needs to have a semicolon, but in Rust, you can get rid of the semicolon of the expression. I'll get rid of the expression, get rid of the semicolon from the one statement, and use that as expression to return the value. That simplifies the programming side a little bit. With all the statements, we now start building blocks of programming units that we want to do things we want. So theoretically, I believe, probably several decades ago, someone proved that with if statement and the looping constructs, when I said if, those are conditional statements, and the looping constructs like while, for loops, you can implement almost all the functionalities in the business world. And I believe I forgot the name of the author who published paper. When he was publishing paper, he was trying to prove that a go-to statement is not needed. And then it turns out to be the milestone paper for structured programming. That's when the Fortran, structured Fortran 1490, and all the other later version of different high-level languages following this instruction and building this structured programming, paradigm. And that's how a lot of programming languages are following. Rust is following the similar paradigm. Basically, Rust itself is a general language. It's able to write almost all the things you want. Could it be writing system level? Could it be to do all the other things? It's a general programming language, not targeting just for numerical computation. And the basic procedures that we are following using Rust is getting your statements ready and rearrange them, put them into different blocks. And these blocks could have branches. These blocks could be iterative. It can run many, many times. By putting all this together, theoretically, you're able to implement anything you need in the business, whatever business logic you might have. Could be mathematical computation, could be some transactions in a bank or anything. So that's the power of this so-called structured programming. And the functional programming is a different paradigm. So that's something we'll not be covering. But the good news is that the developers or the designers of the Rust, they have the background in the functional programming. They know those Lisp and OCaml and Hackshell, those pretty well. So they combine some latest features of functional programming into the design of Rust. So you can leverage the power of structured programming with some functional programming, benefits. And that's what Rust is, which is, I think Python is going to that direction, and Julia is going to that direction. I'm not sure about C++. Latest version of C++ might be going into that direction as well. But Rust is quite unique here in the sense that it's focusing primarily on safety and cybersecurity and give you a very clear direction about what Rust is going. Again, if this is almost identical to C, C++, Python, not much to talk about, if, else, and else if. And it's just working just like a regular if condition. Not like C here, you don't have a parenthesis for your condition. You just put the expression to evaluate your condition directly after if. You don't need a parenthesis. But whatever your code needs to be executed needs to be put into a curved parenthesis. That's kind of like C. And in Python, you don't need a curved parenthesis. Just if something happens with a colon, and that's a condition with with extra space, you are done. But for Rust here, you just write it with a condition and the parentheses, and everything else is just identical to all the other languages, nothing more, nothing less. The major difference is the match statement, which is something like, I'll also skip this one. It's just if else, which is exactly the same, nothing more, nothing less. You don't want to overcomplicate things, in your mind, because you may think this is different. It's just same. It's just probably the way how to write it a little bit different, but it's essentially the same if else statement. The same for else if, it's just trying if you have multiple branches. If condition 1, else if condition 2, else if condition 3, else if condition 4, etc. until to the final state. If you cannot capture all the possible scenarios, let's do the else. That's your final exit. That's the else if statement. The thing I want to mention here, is that the match. Match is what? It's a switch. Those of you who are familiar with switch in C and C++, you're probably familiar with it. Python doesn't have such a statement. It doesn't have this switch. I'm not sure what's the best way to match this. Probably you can write your own structure, but you don't have such nice switch a certain numerical value or conditions. You have different cases, and then you have a default in C and C++. You can do that. So you can have a very nicely organized branches in your code. You can directly see all the channels, possible channels for the incoming data flow or logic flow, and you can see things going nicely. I hate this if else and else if kind of, sometimes you have multiple conditions, multiple channels to go through, and it's kind of confusing, actually it's on the source code level. And the match is trying to mimic the way how the switch is working. It's very similar to switch, but it's a bit more powerful in the sense that it can match the patterns and with a pretty powerful matching mechanism. And also the statement itself is very flexible and give you different ways to do the matching. So essentially, it has an extra symbol, and instead of a colon after cases, right, like C++, it has a pattern with equal sign and greater, which is an arrow. as I'm showing to the right here, you have an arrow pointing to a particular action for different patterns. And the default one is underscore here, which is exactly the way how we use in Python. So this underscore acts as a catch-all pattern. Anything, as long as it's not matching all the previous branches, I'll catch at last. That's the underscore pattern here is about. So it's a carry out some default action based on the pattern it's matching. And also this matching, just like cases or switch cases kind of scenario, it's a first come, first go. Basically, if whenever it matches the case, it'll go out, it'll leave this block. And that's exactly the same case for this one. If you match putting value, it's match the particular pattern, it's go out, take the particular action, and it's leave this block, go to the next block in your code. And again, this is almost identical to switch, but just like the pattern matching mechanism is a bit more powerful and give you a pretty nice way to organize multi-branches in your logical flow. And this is the one example. You can copy paste this. I have all the main there, so you can directly copy paste it and run this in your playground, on your playground. So you consider you have a enum, which is have 4 directions, and then based on the direction, you do the matching, and you print a statement. So enum, enumerator, and match, these are pretty commonly used together, and you can for different scenarios, logical scenarios, you can have all the possible scenarios, matching conditions written down in the enum as a new enumerator, and then you do the matching one by one. By doing that, your code will be much more organized. You can have a very fancy if else whatever breaking you're doing, but even though this might take more space, but it's very clear. Even for brand new programmer, they can look at this and directly see what you're doing instead of getting into complicated if else conditional statement. So that's why I prefer match to combined if else statement in most all the languages I'm using. Whenever I can do that using match or switch, I'll stick with that instead of using if else statement. So again, I mentioned about the if and else and a switch. Those are so-called conditional statements that will mostly control your logical flow. Now, computer is good at computation only when you have a lot of things to be done repeatedly. That's where the iterative logic is useful here. If your computer can only do one thing and always keeping branching out to find a different thing to do and without repeating, your computers will not be running very efficiently. In many cases, you want to put everything together and send it to a computer, and the computer can do all the things all at once. You don't want your code to be dominated by branchings, which actually make it pretty hard to maintain and run. You want this repeating iterative logic be the kernel of your code. That's what a good computer is really good at. You probably, if you have done any parallel programming, in many cases, people are trying to flatten out those conditional statements by evaluating all the conditional statements as numbers, and then they use those numbers to help, either multiplying certain numbers to give you 0 or non-zero, and then you can go forward without, getting into all the conditional statements. And there are many tricks like that. So the whole purpose is trying to reduce all the possible branches as much as you can, and put everything into iterations, which is very good for computers, GPUs, CPUs, IPUs, whatever you are using. They are very good at dealing with iterative logic. So in Rust, there are 3 looping variables, I would say keywords, I'm sorry, here, looping keywords. In Python, we have for, we have while, we have do while, I'm sorry, we have do while. C, we have, I think we have do, we have while, do we have a do in C? We have while and for at least, while, do while. Yes, I think we have do, right? So here, there's a one extra keyword here, loop. To me, actually, I think a loop is equivalent to while true. If you just replace loop with a while too, everything will be working just the same. But I didn't check why they introduced loop here. There might be some reasons, the reasons I don't know yet. But to me, replacing loop with a while too will not change anything. So, but anyway, so loop itself, it's an infinite loop. So it must be explicitly broken. Okay, you can use that with while, do that with while, but it seems to be an extra keyword in Rust, then you can use it to do the loop. While it's just like while we were using before, while certain conditions satisfied, we'll do this. So the major difference between while and for is that we do this evaluation of the condition first. While some condition is satisfied, then I go into. For is kind of different. For loop usually just directly get into the everything inside the loop and then evaluate the condition at the bottom of the loop, or until everything inside of this current parenthesis got evaluated, then evaluate the condition to see if you want to get into the next loop. For is used mostly, as you might know, when you know how many iterations you want to go, or you know how many elements you want to traverse, or for certain iterations that you have some better control, the range. For while, it's usually when certain conditions is satisfied. This condition could be numbers, could be the same as a condition for loop, but in many cases, this could be just a mathematical evaluation. You might consider, hey, when this particular criteria is less than 10 to the minus 3, I'll stop. You don't know how many iterations you need to go. And you don't want it to treat it that way. Sometimes you can just use a for loop, say, I want to for loop like 1 million times, but I put a conditional statement inside my for loop to do that, which could be easily replaced with a while loop. That's why the while loop itself actually makes sense, because you don't need to do any iterations. You don't need to count how many iterations you're doing, like what the for loop is doing, right? So they use it in different scenarios, but again, depending on how you use it, they are interchangeable. There are multiple ways just to use one for the other in the conditional, or the other for the other one. So you can interchange them, but just different coding programming style. So with the loop, it's just getting the let's see, getting the while true loop ready, and then this will just do the exact same thing. But you need to make sure you have the break statement at some point to break. Otherwise, this will keep running. So your code will get stuck, and you will be killed by the system after a certain period of time. So also you can break out with a value, so you don't need to have any return statement, anything like that. You can, when you break out, the loop will automatically return the value from the break to the left-hand side, whichever you have. So loop itself could be simply containing multiple statements, or could have a conditional statement that can give you the value through the break statement that you have. So break and a loop, they're usually getting one with each other. When you have a loop, you have to have a break. Otherwise, it'll keep looping. And a break is it's optional for while or for. You can also use a break in those two iterative logics, but you have to use that in loop. Otherwise, it'll be a dead end. So while it's just the same as what we did before, you can have the conditional statement written, but you don't have a parenthesis, unlike C. And you don't need to write a do here, which is required in, I believe, while, do while in Python. And for is kind of similar like what we used before, but the iterators here could be in a different way, like 1.4 is just iterating like numerically from 1 all the way to 4. And that's a different way to writing iterator. You don't need to use range function or arange function just to generate an iterator. But again, the syntax itself is directly readable. As long as you're familiar with C or Python, you should be able to understand what this for loop is doing. And it's usually used to iterate through arrays and a collection of different elements so that you can process them iteratively. That's exactly what the computer is good at. By combining this iterative loop and conditional statements, you can build a very complicated business logics and to do your work. That's exactly what the program is most about. When you look at the code, the majority part of the code is doing this compilation of the cooking this spaghettis of iterative logics and conditional statements. So enumerate in the loops, you can use that to return both index and values. It's kind of like in Python, we have this function that you can use to speed out the key and value of dictionaries, right? You can do that in a similar way here in loops with the enumerator. So these are the basic comparison of these three loops. If you're familiar with other languages, this should be straightforward. Shouldn't be that complicated to see the difference. And next, we'll jump into the functions. We talk about data type, variables, statements, and all the building logics, right? Those are essential for you to get anything working. The next thing is about functions. In Julian, and now there's more and more in Python, all the functions are treated as we call first-class citizens, in the sense that you can pass the functions, you can use them for many other things, and then you can use functions to build a very complicated structures. Functions are the building blocks for many languages. In C, functions is just the building block for all the libraries, all the tools you're using. You have a main function, everything else could be written as a function. And then just calling all the functions, you get all the things assembled together like a nicely organized, a piece of work that can get the things done with a component structure, different structures. But all the building units from the program perspective, they're all built up based on functions. So in Rust, we use fn function to define function. And it has a returning type. You can define the returning type of the function using this dash greater than symbol. You can point it to the return value for the particular function. And in the latest version of Python, you are encouraged to do that as well. But I'm a Python 2. I started with a Python 2, so my Python programming is pretty lousy in the sense I don't put a lot of effort into following all the encouraged recommended practice. But in Python 3, especially the latest version, getting more and more tools. Okay, so we have the functions for the function names. You want to use so-called snack case, which is it's a way people call this, how you call this naming conventions. You have two words with connected by underscore, kind of like a snack case. That's the way how the Rust functions are mostly named. It's a recommended practice for programming. So Rust doesn't support the default value, or like what Python is doing, and also C++. You can have a default value for certain statements and optional statements, arguments in Python. And Rust doesn't do that, but it supports there's an option type you can use. I believe we'll have something about that a bit later. We'll not get into details here, but there's some extra features that Rust can support whenever you have any default value you want to initiate before the user sending you the input for your function. You can use the default value. And also functions can take parameters, and just like other functions we learned before for other languages, you have very specific data types. It's a strong typed language, so you needed to specify the type of the input value so that during the compilation state, it can check if the type is correct inside of the function. And during the runtime, it will check if the correct type is used when you call a function. And also this could be, the input check could be done if you have all the functions already inside of your source code, instead of calling some other libraries, right? It's different. If you already have everything in the source code, it's able to check if your functions are your parameters, input arguments are correctly typed. And the function can also return values. And the return type also needed to be specified with this arrow symbol I mentioned. This is different from the match arrows. This is with a dash or minus sign. That one is an equal sign. But both are like arrow representing arrows. And kind of like Python, Rust supports a closure, which is an anonymous function, like a lambda function in Python. You can use that to. I'm sorry, there is some question. Okay, we have the slides shared with everyone, so feel free to take the slides and start try things out yourself. So, okay, thank you. And you can use a closure to define this anonymous functions inside Rust. There is also a special symbol here with the two vertical signs, like absolute value. That's what I call it, absolute value, but it's just vertical pipes. You use them to put the parameters inside, and you don't put your function name to it. Especially you are using this to define an anonymous function. You don't need to have a name for that. And it's pretty common use in a similar scenario like what lambda function is in Python. Well, you don't need to define name. Of course, you can define name, but sometimes you don't need to because you just only need this once. And you want to get it done quickly, you just put vertical pipes there and you can define your functions in that way. And a closure can have 0 or more parameters, and then Rust can infer the types of the parameters and return values of closure. But also you can specify the return types yourself. And also that's a recommended practice. You don't want the system to keep inferring. If you can always put the return type directly for the closure and make it more explicit than implicit. And Rust allows definition of high order functions in the sense that you can have a function of functions. And that's when I first talk about it in Rust, you treat a function as we call first class citizens, in the sense that you can pass functions as an argument, and you can call functions inside a function. And it's a pretty powerful way to build your complicated business logic if you need it that way. And also sometimes in many cases, people use functional functions is to make their code more readable actually. It sounds like a weird, and people may consider this like, a bad idea because you may make your code look more complicated. But in some cases, when you have some function calling by itself, actually it's using this kind of syntax will make your code more readable. It's just directly mapped to the way how it is in the real life if you have a function calling a function. So that also allows Rust to support this functional programming patterns, which is very important. As I mentioned, Rust was highly affected by OCaml, and some other functional programming languages. And some features actually built into Rust is just to support functional programming patterns, which is making Rust actually more powerful to dealing with different scenarios with different programming paradigms. And function pointers are used for regular functions, and you can use function pointers as well. And just like how you use the function pointers in C and C++, you can pass a function pointer, which needed to be explicitly typed. And also the arguments also needed to be explicitly typed so that you can use the function pointers without violating any other strong requirements for the types. And you can use function how to call the pointers to pass the references to different functions like closures, and the type of the function pointers is usually is fn, or which is a function type, or it's a function type mutable, which is fn mut, and a function type once, which is just calling this function just once. which limited the number of times, how many times you want to call this particular function. Those are advanced features. I don't think we have time to get into all these details, but I just want to put it here, make it accessible to you all, so you can these features are there. If you want to use functions as pointers or doing functional programming, Rust have all the support building internally. So last, I want to cover some advanced topics, and mostly the ownership, which is one of the main reasons why Rust is considered a safe programming language. Lifetimes is mostly controlled by the ownership, and actually part of the ownership is relevant to the lifetime, because when you are not owning this particular part, or you're going out of your particular scope, your lifetime is ended automatically. So you can specify your lifetime with tags, but in many cases, many because the extra burden of typing and things, like you use the scope to control the lifetime, and we'll get into that. But again, the Rust give you the fine control of individual variables, individual functions, about how long and you want to survive in my program, which is kind of sound like cruel, but that's the way how this better control is for certain functions, which might be violating those some rules, and getting the problems, produce some problems when it's running out of its lifetime, and have some hanging or dangling pointers somewhere, which will be the potential cybersecurity issues. So next, I'll also get into error handling and traits and trading objects, and I'll get into what the traits are. We talked about this a couple of times already, but I didn't get into the details. And then we'll talk about generics, which is also something new. At least the term itself is something new in Rust, but the concept, as you'll see, actually could be mapped to something we already know. And then lastly, I'll talk about the standard libraries that the Rust community is providing, which is pretty powerful. And at least, as we mentioned, it's a small compared to Python's library and C++ library and C standard library, but it's already providing all the fundamental building blocks for you to build something big. So first, let's get into the ownership. So the memory management system of Rust is built around two key concepts. One of them is ownership, another one is borrowing. So the ownership, it's very strict defined inside Rust. Basically, one value has only single owner. When you define another variable here, variable and value, they are like a pair. Variable is, it's more or less like you consider variable is like a container. It's like it's owner, and the value it's whatever the owner has ownership to, and they have a one-to-one map. So whenever owner disappears, the corresponding value will be annihilated in the system. And when you switch the owner of the value, the previous owner will be detached, or at least this previous owner will not have ownership to this value anymore. So that's also why this I'm sorry, this should be S1 owes a string here, not S. So S1 owes a string here, which defines a string. This string is defined from this literal hello. It's converted into a string type. So that's why we use a from function. So this S1 is defined as a string. And then when you define a new variable S2, it will change the ownership of this string from S1 to S2. And S1 will be disappearing from the system because S1 is not being used anymore, referring to anything. It's dangling, it's dangerous. So the system will forget about S1, put it into the, somewhere, you never know. And if you use a special function of the string, which is a clone will do the deep copy, which will copy the not only it will copy the string. Basically, you have a double copy of the string, two copies of the string. One of them is two of them are identical, but it's storing at different locations. So S2 will be pointing to the new location of this new string. That's how you do the deep copy. So S2, when you do the S1.clone, you'll get a new copy of the string. So you can keep two strings, S1, S2. Basically, when you do this clone, you'll have two strings in your memory. So you use double the memory. And if you let x equal to 5, and then something happened, your which is kind of different from the previous one. And if you want to, for example, let x equal to 5, you're define this variable x, which owns this value 5. Okay. And this max copy function is an extra function I put in here. It's nothing more than just utilizing this function. But the reason is that whenever we start using this integer variable, a default copy function will be triggered. That's implemented for all the integer types, which is different from the string. String doesn't do that. String doesn't have this clone function default whenever you try to call that function trying to do something. But when you try to use this particular variable inside any function relevant to the integer, it will take this integer and create a copy of that and use it. Okay, so the integer type is treated different, mainly because there are built-in function to create an extra clone for that. So you probably don't mind to have an extra copy of the integer, but sometimes you do mind to have an extra copy of a very long string. That's probably the logic behind this. So if you want to have an extra copy of the string, you have to do this clone and do the deep copy. So another benefit of this ownership thing is that whenever something's not used anymore, the system is safe to clean it up without worrying about any dangling pointers or anything, because the ownership is only assigned to a single, the value is only assigned to a single owner. You are not supposed to be affecting other owners' value by removing this particular owner from the system. The owner here, I'm referring to the variable that we defined here. Okay, so slice, as I mentioned, is kind of different. It's enables continuous reference to a continuous sequence of elements in a connection. And it's not only give you the starting pointer to the array that you want to refer to, but also the bound. So the slice contains the whole packet, not just the starting memory address. So that's a major difference for this reference symbol that we used. I already talked about this a couple of times previously. Now, borrowing, it's kind of like referencing. If you just look at a symbol with this AND symbol, that's how you extract the memory for the particular variable in C. Giving me a T, or also in Python, you have the similar idea. You give me a variable T previously defined. The AND T will give you the reference. Basically, you grab the pointer pointing to the address that holding this particular variable. And now, if you want to make this mutable, all you do, you need to add the mute keyword after this AND symbol. So you have AND mute T. So this will make this borrowing mutable. So you can go inside and modify whatever inside of this address. So by default, when you're just borrowing, you just have access to the value located at a particular address, but you are not able to change anything. That's the immutable, which is a default borrowing. But if you really want to declare your ownership, you want to use it, and you can do it using this immutable borrowing. Okay, so this definition is kind of like a let and let mute, in the sense that when you define a variable, you have to explicitly tell the system, tell the compiler that I want to modify something inside, and the system will allow you to do it. So by default, everything is immutable, even for the references or borrowings here. It's by default is immutable. So you can copy and paste this and run some example. You can change some settings and see if it behaves, like what you imagined. So for the mutable borrowing, you can modify that very similar to the way how you do reference in C, because when you the function calling, when you are calling a function, that when you pass your reference to the function will have access to the memory address holding your variable. So the function can do anything, the function wants to the particular address because it had full access to your memory block. And you are giving the full control over to the function you're calling to modify your variable. But here, you only allow the function to do that by defining the mutable borrowing reference or mutable references to the string. So again, it's similar. It's just like you need some extra mute symbol just to make that happen. Otherwise, everything is immutable. You can read it, but it's not writable. So lifetimes, refers to the duration of which the reference is valid. In most cases, you can define the lifetime just by adding extra parentheses, curved parentheses. Anything going out of the current parentheses will be considered as out of the scope of my current variable, and I'm not available after my scope. And more or less like building this house for yourself. I know it's kind of like cruel, but let's say no, don't say it for yourself. Build this house for some abstract animal. When this house is broken, when you're going out of this house, the animal will die. Okay, so that's one way to add the scope or lifetime to the particular statements or variables for your statement. Just adding extra parentheses, curved parentheses. That's the probably easiest way. Another way you can define the lifetime is to use so-called lifetime annotations. It's like a tag, tag to some variables. And you want your system, your compiler to understand that this particular variable or particular function or particular parameter can only live this long as represented by this A. So if you, this A actually is defined as scope because you need to define this A outside of this parentheses, curved parentheses, and anything inside this curved parentheses will live as long as this A is still valid. So you are defining a lifetime for the variables inside your scope. And you can define multiple scopes for variable A and variable B. Variable B, you can define, different scopes. And there will be live as long as this lifetime annotation is still valid. Okay, this gives the compiler the direct power to check if your variable is valid under a certain condition. Which actually this particular annotation makes your code really, really, really hard to read if you don't, you're not familiar with Rust. And that's also the part when I first read into the Rust code with all the annotations and all the whatever mutability, deflation, whatever. I couldn't get myself mind cleared about what this whole sentence is talking about or whole statement is talking about. But you needed to get familiar with this. But again, as from my own perspective, I will try to avoid using all those tags by using those parentheses to insert different lifetimes. But again, that one is more limited. This will give you the full control of individual variables and parameters inside your given scope. But again, make it harder to read it unless you get used to this, this kind of annotation. So there is also, again, the Rust developers or designers they are smart people, so they define the so-called elision rules. So what they say is that Rust can infer lifetimes, and as long as certain conditions are satisfied. For example, if each input reference gets its own lifetime parameter, I can infer it from your scope, basically parentheses. If there is exactly one input lifetime, it is assigned to all the upper lifetime. So that could be inferred. So the lifetime, as long as it's giving me one, the same lifetime, and the lifetime for the output will be the same. And it will be applied to all the output lifetime. And that's actually, more or less like getting back to what I said. If you have a clear idea about how long you want your variables and parameters to live, put a parenthesis, curved parenthesis around them, and you have a clear image yourself without Rust to guess, by using this elision rules, because that more or less like extra parentheses when you try to do the arithmetic calculations. Those are redundant, but it gives the compiler and yourself a clear picture about the priority. Probably for compiler, it doesn't need it because they already have the priority rules built in, but it'll helpful for you to see the lifetime yourself by putting the parentheses around certain statements that you want them to live in this particular scope. Okay. And in C++ and C, you have a similar scope problem. Unless you define some variable at the top, it will stay alive. But if you inside a very specific scope, it will go out unless you define that. You can define new variable inside this scope. Curved parentheses inside C and C++. It has a similar lifespan, just like what Rust is dealing here. So when you define the scope of your variables in the class level, when you define public variables or private variables in your class definition in C++, that's a different level of scope. That's not just a lifetime. That's more or less like the protection of the accessibility. And that's kind of different from the lifetime here. Lifetime here, it's mostly about internal logic and evaluation. And the other definition for classes like public, private, protected, those are for external access to the information internally. So it's a kind of different concept. But here, as far as lifetime is concerned, it's good to keep your variables life as short as possible. The reason is that given the short lifespan, you are less likely to expose your information to the outside, because whenever you get it done, throw it away. Use it as a one-time, because this is a virtual environment. You're not damaging the environment by throwing away and use one-time variables. And the system will recycle the extra variables and extra space and use that for something else. So you don't need to worry about that for writing the program like this. Even if it's one-time variable, it's okay. System will handle that. But again, you don't have to do this for this. It's just do this because of your business logic needs such features, and then you want to minimize the exposure of the information, after certain operations. So things are getting a bit more complicated when you're dealing with the structs. And for structs, when you hold the references, their lifetime must be annotated. And because you're holding references, you're trying to get access to outside, to the more or less like to the pointers, to the variables, to the values. You have to control your lifetime to carefully detach yourself from any potential modification you may make. Again, you are protected by the mute keyword, because if it's an immutable, you won't be able to change anything, but your information will be exposed because you have access to the external. If for some reason you don't have a careful defined lifetime, hackers might be picking into the structure and looking into some other data passed into your structure. So that's a potential vulnerability that people, at least the Rust programmers or developers, are trying to avoid by explicitly requiring you to define the lifetime of your structs, especially when you have references. So next we'll get into the error handling, and essentially we have two types. One of them is just using this results, which is have a two types. One of the T is means the general type. E is error, whatever error code is returning. So you can use the enum result to handle the errors. Or another one is to use a panic, which is a macro, panic macro. So exponential symbol panic, that's a panic macro will handle this and create an error message for you. Just like what you see from the compiler, something like that, give you an error message saying something goes wrong and print out a statement. In Python, there's a log function, log module. I use it a lot just to capture the errors, print out information, print out debug information. Kind of similar. When you have a log error, you more or less like print out the error message and it exits the code, and that's how you handle this panic situation, which means that you want your code to stop. Something bad happen. The other one is mostly about more or less like a switch and like a try and a catch kind of or exception catch kind of mechanism. And there is one example here. So you do this catching yourself by returning the either error okay, but both are types of the result. So your returning will be the result with the output type that you are assuming you're starting your division function. And then you start want to add error capturing. How you do that? You return this function as a result enumerator, which is a predefined enumerator. And in your output, you wrap up your output with error and or OK function. By doing that, your output will be automatically handled by the result return, and the system will get the exception captured and give you the right output. If your result is okay, if the divisor is not 0, you'll get the result calculated. It's okay, and the result of getting back to the original type. So you'll be seeing the quotient from your calculation. Otherwise, you'll get error message. So you can try this out, and it's a Rust way to do the error capturing. So next we'll get into traits. It's like it's similar to interfaces to other languages. In Python, you can define interfaces. C++, you can define interfaces for your class. When you define interface, you don't define your implementations. The implementations could be defined, it could be not defined, but it does define the interfaces for others to implement the particular functionality for your class. That's exactly what interfaces are. And these traits are something is defined in something similar, but it's defined separately. It's not like a combined together in one big class. You define these traits separately. So you could implement this summary for particular structure. And the summary here is the summary you're implementing. That's your traits. And these traits could be implemented with the summarized function. The summary itself is the trait, but the real implementation is done with the summarized function. Okay. And you can do the same thing for a different structure, but using the same summary. And as long, whenever this summary is called, and it will be trying to find the corresponding type and get the right function called. So it gives you the reusable function like the summarize, which could be written down separately. And then when you write your code, when you want to write your code to get a summary for different types, for example, news article or tweet, you can call the same function summary, but implementation could be separate. They could be implemented separately, but the same interface will be there. So the same function summary could give you a summary for either the news article or tweet. So that's a power interface. You don't need to change the name of the function, or I'm sorry, here it should be called a trait, but it can handle different cases. To implement the traits, it's defined by a trait keyword, and you implement the traits are defined using the trait keyword. You can implement that with the define the trait. Define the trait, and then you define this function, implement this particular trait for the particular structure, and the same trait could be recycled, used by by multiple for different structures. Again, the structure is nothing more than a customized type, so that means you can define this trait for different types of data. And also, one single trait can contain multiple methods, and you can deal with different methods with the trait. So trait is like a connection of the methods, and you can link these traits to different objects. Different structures, and they can handle all the traits can handle all the structures separately. And the object itself is the trait object. It's kind of like getting abstract to abstract, which makes things more complicated. But what I'm trying to say here is the trait itself could be used to define the objects itself. So trait could be treated as a type, and you can use the trait to define objects, and that objects will be used to perform other tasks, and depending on the particular function call, etc. So these are more advanced features. You can explore this more when you get into the production Rust development. Generics are functions that can accept parameters of any type. It's kind of similar to C++ templates. You can use generics to write a function that accepts all kinds of types, can implement algorithms, which could be dealing with student records, could be dealing with customer information, etc. As long as the algorithm doing this, for example, the sorting, etc., could be as long as you're providing the particular methods for me to do the comparison, right? For certain sort algorithms, you can implement a sort algorithm using the template. Here, you can use generics in Rust to implement that. So, for example, this is the one generics that I'm using here. Could be the point represent using either integers or floating point to handle my point. For example, if my point is representing a pixel on a screen with x and y, it's just number of pixels along x and y, I use integers. But if it's point to some xy in a real xy simulation, a 2D simulation, I can use point here for with a floating points for my points positions. So I can use this generics to handle points in different scenarios. And for enum, it's the same. I can define this. For example, the OK and error. This actually it's a generics that enum is defined. Enumerator is defined. So this result itself is a generics that we have been using for our previous one of our previous slides. So we have probably 5 minutes left, and I assume you all be able to copy, paste, and run things on your playground and test things out. If it's working, it's great. If it's not working, it's also a learning process. You can try to tweak it around to see how it's working. And essentially, the error message itself should be very, very informative. One of the major benefits of Rust, of using Rust, is that you can get a very informative error information, error output from the compiler. And using that, you can fix your code quickly. That's what I did. When I start learning Rust and just get the read error message, I can directly figure out where the problem is, which is a big, big headache when I try to use a C++ compiler, which is a very big problem for C++, especially when you start using templates, generating types, and doing some other things. And the error could be traced back all the way to the very big stack, and it's kind of hard to follow the errors. But for Rust, it's relatively easy. So with that said, we already talked about almost everything needed to get you started to do a non-trivial Rust project. But to really utilize Rust in full, you need to get yourself familiar with the Rust standard library. So from here to the end of all the slides, I have some examples. I tried them, I explored those, but I just tried to show you some simple examples using different Rust libraries. The most important ones are the ones dealing with I/O, file system, multi-threading, and time management, collections, different collections like containers in C++, and the system environment. How can you get a system environment information? How can you do the synchronization and other stuff? And all these are fundamental building blocks for Rust projects. So, just like when you're learning Python, actually Python itself is simple. You probably spend most of the time learning different modules inside of Python, right? Similar idea here. When you start building things more and more complicated, you'll be spending more time learning Rust libraries, standard libraries, or some others modules, right? Shared online. You can download them and use them. For I/O, it's straightforward. You have a standard in, standard out. Those are very similar to C++. Standard out is your screen. Standard in is your keyboard, and that's how you read and write. But I'm not sure if you can do the standard in and read a line from the playground, but give it a try. We might have the input type, but otherwise you should run this on your command line interface. So you'll see it will ask you to input something and it'll print out something for you. So file system is just reading and writing, and it's very similar to C and Python. Actually, you need to create and all the other manipulations. For all this kind of method, you have CRUD methods, CRUD, create, read, update, and delete. And all these are basic functionalities provided by all these operations for strings, for files, for objects, anything. So it's called a CRUD functionality, CRUD, which is something you're looking for when you start learning all these libraries. Thread is the same. You have a CRUD for thread. You create a thread, you spawn a thread, and you kill them. But again, there are some other operations you can do with the thread. You can join the threads. What else? You can create a mutex thread, so that you can do a lot of fancy things with standard threads libraries. And the beauty about thread here, you don't worry about the racing conditions as long as you're following the rules that Rust asks you to follow. Immutability and ownership, lifetime. The thread here you're writing here will be a very high quality multi-thread program, and that's the whole point of getting everything, all the hard work done in defining your variables and define the scopes and ownerships. The whole purpose is just trying to use libraries like this to get your code safer and high performance, right? And there are also time to measure the time, etc., and also collections, just iterating through different collections, hash, and other things. And you have an environment to give you the arguments or the information from the system environment. And it's almost the same thing you get from the Python environment module, and you can get similar things here. For synchronization, you can do async and async and how you want to synchronize. Again, you'll also benefit a lot from the ownership and immutability functionality of Rust, so that you can do a synchronization much more with more confidence, so that you don't worry about anything about any racing conditions and other memory safety issues here. And lastly is about safety error handling. Already mentioned about this. You can use this built-in error handling mechanism. So with that, let's conclude our short course today. There are a lot of online resources you can leverage, a lot of free books online you can refer to, but I think the most important one is the books that from the Rust official website. And hope you all learned something about Rust today, and hope you all get started working on building your first Rust project and run on ACES. Thank you so much. So lastly, this is our survey for the short course today. I'm sorry for the rush, but with 2.5 hours, I think it's barely enough for you to get started with the Rust. So we'd like to hear from you all about what you want to learn in the future. And again, I'm getting myself a better Rust programmer myself, and I'll probably start doing some high performance computing related programming project with Rust. So we'll probably have more courses like this offered in the future. So we do want to hear your opinions and your what you want to do. Thank you all so much. And if you don't have any questions, I think we can end the short course today.